Well, hello there, General Physics. Let's get some review going on for our first semester exam. So this is going to be an interesting exam. As you know, we've based it off of James and the Giant Peach, which is a book, a children's book. You should have a copy of that. And we're going to be using that as the basis of our questions because there's just so much good physics in there, which I know sounds a little crazy, but you know, I am a little crazy sometimes. What can I say? In any case, your review packet. If you're struggling or want to just check your answers, this is going to be the way for you to do that. So let's get started. I have a lot of slides here, 17 to be exact. Good Lord. But what I've done is taken each question and given it its own slide. So we have plenty of room to write and get things done. Some of these will go fast and some of these will go slow. So let's get going. So number one here is a position time graph. Notice I have X in meters over here, and you can tell that I have a nice linear relationship here. The key thing that you need to remember about these graphs is that the slope is the velocity. Okay, the slope of a velocity time graph is acceleration. The slope of a position time graph is velocity, and this is a constant slope. It's going up evenly, which tells me I have a constant velocity. So when I go to figure out the average velocity of my object, I am very simply getting the slope of the line. And this one, you'll notice, does start at time 0, but it does not start, oh, what am I doing? Silly Grady. That should be an X, and that should be an X. Silly Grady. All right, but my initial position is not 0. So let's keep that in mind. I took the endpoints, but the truth is you could pick any of the points that would be easy to read. So I chose this point right here and this point right here, and I'm going to find the slope of the line there. Oh, I'm writing down the, no, I'm not. I'm not writing down the wrong things. I'm doing just fine. Thank you very much. Good gravy. I kept getting interrupted while I was doing this by my dogs, believe it or not. I have a diva who wanted only to have me pay attention, and she did not like the fact that I was busy doing physics. All right, write a mathematical expression. This is looking for an equation of the line using y equals mx plus b format. Not new, but definitely a helpful thing for us. So what you want to do is replace whatever, not an S. Man, you can tell it's Sunday and I should not be at school, right? Whatever is you're measuring on your y value or on your y-axis is going to go here. That is x in meters. M is our slope of the line, so that's 8.3 meters per second. Then what are we measuring on the x? Time in seconds plus our y-intercept, which is the value of y when x equals 0. So there you have it. Those are the first two. Those are my first two. Okay, next. Shown below is a velocity versus time graph for an object. Describe the motion of my object. Okay, so here you can see that my velocity, which is on the y, is constant positive velocity. It's 4 meters per second. And then here, it rather instantaneously changes to a negative 3 meters per second, and then again rather instantaneously changes to a velocity of 0. Now in reality, we know that that cannot really happen, but we are just going to work with it for a few seconds here. All right, we're going to get to acceleration in a few of these. So we can really graph anything we want, and it's the bottom line. So let's consider, if I want to describe the motion, tell me how this thing is moving. All right, so it's moving with a velocity of, let's say, 4 meters per second for 2 seconds. So it's moving to the right. Yes, positive velocity means I'm moving to the right or moving in a positive direction. Generally that's to the right, but let's be clear, it could go either way, right? We could have something, we could also say it's moving up. All right, so then it turns, moves to the left or in the negative direction for 1 second, and then it stops. And that's pretty much it. Then it stops. It just stops on moving. All right, so I guess if you want to get more specific, you could put in the velocity here as it's moving to the left. But that pretty much describes the motion of our object right there. Okay, still on position time graphs. Still on position time graphs. When we're dealing with constant velocity, there's not a ton of variation here. There's only so much you can do. All right, so find your average velocity from 0 to 10 seconds. So here's where 10 seconds is. 0 seconds is here. Again, it's a constant slope, which means I have a constant velocity. And it's a negative velocity in this case, and this one's going to give me a positive velocity because my slope is positive. Now, you can pick any 2 points, but why not work with the ones they give us, right? So the velocity is going to be final position minus initial position over time final minus time initial. And I'm going to use the same formula down here for this one as well. I'm just going to have some different numbers. Okay, so let's consider my final velocity is 10 meters per second, my initial is 30, and my final time is 10 seconds, and my initial time is 0 seconds. I'm being naughty there and leaving all of the units out, but I usually give you guys a little bit of grace there as well, so I guess we're in the same boat. You naturally end up with a negative slope when you do the math properly. Remember, we're always doing final minus initial. That's kind of the key. When we do the same thing from 10 to 20, again, you can stop here. That's fine. I actually went to there because it's the same line and it's the same slope. That's not changing. So don't be alarmed. So again, I did my final position of 25. My initial position was 10. And then my time final 25. I don't have 0 for an initial time in this case because I'm starting somewhere in the middle. So I ended up with a naturally positive velocity that is not as large as the first one. And that makes sense because my line is not as steep. So that should work for us. Okay, on to this basketball question. Basketball travels at 3 meters per second for 3 seconds. Describe the motion of the ball after 3 seconds. Okay, so 3 seconds. 3 seconds takes me here. Okay, so originally the ball here is moving in the positive direction, which we could figure maybe to the right. And so if you're going to, at 3 seconds or after 3 seconds, the ball turns around. Okay, that doesn't look like the word turns. Even on a smart board, that doesn't look right. All right, so the ball turns around. Let's assume it's going left because right is generally our positive velocity. So we're reversing direction, but also it moves more slowly. Right? You notice that up here, I've got a velocity. It's a constant velocity, but it is what, 3 meters per second here, right? And down here, it's only at -1. So it's not moving as quickly, and it's also going the other way. All right, draw a quantitative motion map that represents this object. Now, quantitative means numerical. So let's consider that I can figure out how far I'm going, quite frankly. Right, the area under a curve here, that's going to tell me how far I'm going. So if you figure that this is 3 seconds, and this is 3 meters per second, that tells me that up here I'm going to go 9 meters, and then down here, because that's the area of a rectangle, just in case you were wondering. All right, so this one is going to be a velocity of -1, and then of course I'm going from 3 to 7, which is 4 seconds. So here, I'm going to move -4 meters. So when I consider the motion map, and I even have like my 0 meters on here, okay, what I did in order to fit everything is I decided to make these a little bit of a bigger interval in terms of what each hash mark meant. Now remember, each second is still going to be you know, where we begin each arrow. So let's see, if we started 0, let's assume we started 0, because why not? So after the first second, we should be at 3. After the second second, we should be at 6. Third second, we should be at 9. All right, and we can just draw an arrow in between those. All right, because we're traveling 3 meters every single second. This is where things get a little bit weird because you'll notice I do this instantaneous change thing right there. And while that's not terrifically realistic, it also presents kind of this interesting problem for motion maps. Like we like to have dots in nice linear fashions, but I seem to be changing instant velocity here. So my next dot's not going to be so great. All right, at this point, I start to move -1 meter per second. So I'm going to go from 9 to 8. And then I'm going to go from 8 to 7. And I'm going to go from 7 to 6 and 6 to 5. And I forget how many however many I go here. I think that's where I stop. All right, so this is not ideal, but I would totally understand an arrow like that because you really are changing right away. And then, of course, shorter arrows in between. And that is what your motion map should look like. It's going fast in the positive direction, and then it's going slower in the negative direction. How far did the ball travel from 3 to 7? Oh, lucky for us, we already figured that out. That's -4 meters. Oh, I guess I got cut off. -4 meters, we'll put it right there. All right, what I'm doing is I'm taking the area of this little rectangle here, reading the graph and going with that. So hopefully that helps and isn't too messy for us to read. Okay, new question. Oh, let's go back to black. I kind of like that color. All right, race car reaches a speed of 95 meters per second after it's 450 meters past the starting line. I'm going to begin with a VT graph here because, we figure everything out with a VT graph, and I don't have to worry too much about it being perfect. But basically what this is saying, I assume I would start from rest, and then I reach the speed of 95 meters per second. And it says after it is 450 meters past the starting line, which tells me that the area of that triangle is 450 meters. And then it travels along for the next 12.5 seconds. Let's make my graph a little bit bigger. How far will the car be from the starting line? Okay, so this is still 95 meters per second for speed. The thing that you have to remember is that the 12.5 seconds goes from here to here. Now, I don't know how long this is, but the good news is I don't think I'm going to need it. All right, I just know that that particular triangle or this particular rectangle, the base of it, the length of it is going to be 12.5, and the height of it is going to be 95. So if I want to figure out how far it goes here, I'm going to use the area of my rectangle, which is going to be 12.5 seconds times 95 meters per second. And I'll get 1637.5 meters, which I can then add to my original 450 to get my final answer. Ta-da! Easy peasy. Right, that one worked out kind of nice. Now it's time to start looking at forces. Alrighty, Dodge Dart parked on a hill, and we're given the mass. Draw a force diagram for the car. Technically, I want to call this a free body diagram, and I'm going to do it right on the car because that's not very straight. Went a little sideways there. Sorry about that. All right, we want to go straight down for gravity, or FG. We have normal force going perpendicular to the surface, and you got to figure that there is friction trying to keep it from sliding down the hill because we know that there's a piece of that gravity that is trying to go down the hill. All right, B, what is the weight of the car? I'm going to do it up here because I'll have more space and it's not going to, go off the screen. mg is always how I find the force of gravity. We don't worry too much about rounding, thank heavens. Calculate normal force of the car. All right, so a quick reminder that what we would do is we would take this gravity and we would break it up into its two component vectors. This is the cosine piece of that, and this is the sine piece. So if I want to know normal force, that is going to be equal and opposite to this one, mg cosine of theta. So, and I know they're equal because the car's not levitating or sinking into the incline itself. So I'm going to take my 1150, that's m. I'm going to take 9.81, that's g. And I'm going to do the cosine of 15. Don't forget, you need to be in degrees, not radians. And then when we plug in all those fun numbers into our calculator, ta-da, that's our normal force. And friction force is going to be equal to mg sine theta if this car is at rest. How did I do that? I moved that little bad boy around. I have no idea how I did that. I'm learning all the new fun things about the smartboard. Okay, so force of friction is going to be equal to the mg sine theta. And so again, I can plug in the m that I've been given. I can use 9.81 and I can use the sine of the 15 degrees. When I multiply all those together, I get 2920 newtons for that one. Okay, next. Kind of a conceptual question here. Consider a collision between a small car and a heavy truck. Small car hits giant truck. In such a collision, how does the size of the force exerted on the car by the truck? All right, so how does this force compare to the size of the force exerted by the truck on the car? Car on the truck. Whoops, I labeled them backwards. I should have labeled that one first. Okay, so each of these forces upon each other, they are going to be equal. And you say to yourself, no way, man, because that car is going to get smushed. That's acceleration, that's not force. Newton's third law tells us equal and opposite reactions. The key is the fact that the car pushes on a truck, the truck pushes back on a car. These forces do not act on the same object. They act on different objects. That's why I have two arrows. Okay, so these are equal forces to each other. It's not the forces that really matter, it's the accelerations. And more on that as we certainly get into momentum a little bit later. All right, stick with blue for a bit. Draw this velocity time graph for a ball thrown vertically into the air during an up-down motion. So we're talking about throwing something up into the air and then having it come back down, right? That's exaggerated. Honestly, it doesn't even really look like that. You know, it starts down here, it goes straight up, then it turns around and it comes straight back down. All right, so let's keep that in mind as we go. All right, so we're going to draw that velocity time graph. We are starting with it going up. It is slowing down. I just picked that spot randomly, and then it turns around and it comes back down. Ideally, you'd have it actually hit right there in the middle, right? If you're going to have it come back down to the same spot. Oh, I'm not so good at drawing those right out of the gate. Freehand is a little tough with these, so let's see if I can manage to not erase my other line. Look at how fancy I'm getting with that. Very nice, Mrs. Grady. All right. Free body diagram for the ball when it's at the highest point. What's acting on it? Gravity. That's it. And honestly, that's the free body diagram anywhere. It doesn't matter where in the point of flight it is. That's it. At the highest point is the velocity 0? Yes. Yes, it is. And you know why? Because gravity slowed it down. Little g, your negative 9.81 meters per second squared, that slowed the ball down and then started it accelerating in the negative or accelerating and moving then in the negative direction. But this is that pause at the top. At the highest point is the acceleration 0. No. All right. We cannot shut off the gravity. It would be kind of fun every once in a while, but keep in mind, if the acceleration was 0 at the peak of flight, what that means is that your velocity would not change. So if you got to the peak of flight and the ball just stopped and then the acceleration went away, the ball would just hover. I mean, if it's stopped and there's no acceleration, it's not going to change. So that means you're going to have a bunch of junk floating around in the air. That's not right. You know it comes down and bonks you right in the head. So the acceleration cannot be shut off. We do not have a gravity switch that we can just shut off the acceleration. Sorry about that, guys. We always have that negative 9.81 when we throw something up in the air. All right, let's move on. Let's move on to the next one. Ooh, we're back to position time graphs, but now they are curving. We are getting crazy here. Okay. Oh, written description. Describe the motion of this object. All right, first of all, it's moving in the positive direction. So let's keep that in mind. Okay. Whatever. Just move that little thing around. All right, moving in the positive direction. That is the world's worst handwriting. I am so sorry, people. All right, but what we are seeing here is that it is slowing down. And if you're saying, how do I know? How do I know this is slowing down? Well, first of all, this is a curve. It is not a straight line. It's curving. This is a side opening parabola. And what you'll also notice, except for that last little part there where I went a little rogue, with the line is that this line is becoming flat. It is becoming more horizontal. If the slope of this line is velocity, well, that's where the velocity is going to be 0 because it's going to be flat. So definitely that's not going to work. Oh, I guess my motion map is down off the screen. I apologize for that. You do actually have a little diagram for your motion map. So I guess I'll just draw it up here and maybe that'll help. All right. So if this is your little, motion map, you have these guys, and then you're supposed to have velocity on top and acceleration on the bottom. Keep in mind that your velocity vectors should be getting smaller and smaller. I don't know how well I'm doing there. And stop. That's kind of what I'm going for here. Now, if we're stopping and we have a positive slope, I mean, it's a changing slope, but it's still a positive slope. The line is still going up. So that's why I'm going to the right. Arrows are getting smaller because it's slowing down, but it's also going to the right because my slope is positive. Okay, if this is the case, then what this tells me is that my acceleration has got to be going the other way. I've got to have a negative acceleration, and I'm trying really hard to make these arrows all the same size because it's a constant acceleration. We do not deal with changing accelerations in here. This is a constant acceleration, and it's going the other way. When we have velocity and acceleration going in opposite directions, the good news there is that we slow down every time. It doesn't matter. Okay, so sketch a corresponding velocity time graph. So if we started off, and you'll have to go back to, you'll have to go back and take a look just to double check, but we're slowing down. All right, we're moving in the positive direction. This is why this is a positive velocity. That's not supposed to say TV. That's supposed to say positive velocity. This is negative velocity. This is 0 velocity. So we're slowing down. And then it says, assume the initial velocity is 10 meters per second. Determine the acceleration of the object. So, okay, if this is 10 meters per second and this is 0 meters per second, and if I go back and take a look at my graph, I know that this is 10 seconds. My side parabola has an actual time of 10 on the axis. That's where I'm getting that number from, in case you're wondering. If I want to find the acceleration, that is very simply the slope of the VT graph. So VF minus VI, TF minus TI. All right, and then I can fill in what I need. I should get a negative number without a doubt. All right, my initial time is going to be 0, and I get an acceleration of -1 meters per second squared for that one. All right, next we're continuing with our velocity time graphs. We're going to work with this graph, which has something moving in the negative direction and getting slower. All right, that's where it, that's where it actually stops moving, is right there. Okay, describe the motion of the object. Oh, I think I just did all that, didn't I? Let's assume left is what we're talking about. It's moving left, it's slowing down, and eventually it will stop. Determine the acceleration of the object from the graph. That's going to be the slope of my line, and I should end up with a positive slope because you'll notice my slope is positive, right? It's going up toward that 0. So you might have a negative, and consider negative velocity, positive slope. Ta-da, slows down. That was what I was mentioning before. All right, so my acceleration is going to be VF minus VI. I expanded on this one because what's different here is my final velocity is 0. I still have an initial time of 0, but what that does for me is it gives me the 2 negatives for the velocity. I have to be careful in the top. So I end up with a positive 1.5 meters per second squared acceleration on that. As long as you do the final minus initial and you're careful, you should always be able to come up with the correct sign of your acceleration, whether you're dealing with something slowing down, starting in the 4th quadrant, 1st quadrant, doesn't really matter. Okay, shade the portion of your graph. Let's go back to red. Displacement from 2 to 6. Okay, so 2 is, okay, why are you moving? That makes no sense to me. I don't know what I'm doing to make it move. And the whole thing moved. All right, let's try to get you back there? I don't know. Don't know, but now I've, all right, so there's, okay, nope. I don't know how I'm doing that. That makes no sense. Let's try one more time. From 2 to 6, and I want to know the area. Oh, looky, looky. We're going to have a trapezoid, which means we're going to need a triangle and a rectangle. Oh man, that's not even a great rectangle. I must have slid it just a little bit. Just a little bit. Hopefully you'll see it. It should actually be a rectangle all the way to here, but I think I'm a little off kilter with my maneuvering. So now that we've shaded that in, calculate velocity at 2 seconds and at 6 seconds. No, you are not allowed to just take values off the graph. Do you like how that's been thrown in there? Okay, so let's consider, we are going to really just use this equation. We're still just going to use our slope of the line equation. Okay, TI, you could figure, is most likely going to be 0, right? So let's just, I'm not even going to put a number in here to start with. Let's get rid of the TF at the bottom of the fraction. Multiply both sides. Okay, get the TF out of there. I'm going to move over the VI. VI plus ATF equals VF. Keeping that in mind, I can just use that equation twice, quite frankly, with these guys right here. You know what? I just realized I made a mistake in the previous question. Chances are you found this a little while ago and you're going, Mrs. Grady, Mrs. Grady. But, oh well. Determine the acceleration of the object from the graph. It wasn't 10 seconds, was it? It was 8 seconds. My bad. So my slope is actually a little bit different than what I had said. Oh, thank goodness. I thought I was crazy. But you know, she can't be wrong. She's the teacher. Oh gosh, I'm wrong all the time. It happens a lot. So hopefully you picked up on that and we're just kind of like, okay, I'll just see if she finds her own mistake. Yay, I did. All right, so we're going to find the velocity at 2 seconds and at 6 seconds. So when I consider this graph, I want to take my initial velocity, which is going to be -15. I'm going to plug in that acceleration, and I'm going to take my final time. And if I take care of that algebraic equation, I should end up with a VF. So when I consider my first one, -15 equals, nope, sorry, -15 does not equal, -15 plus, let's try that again. 1.875 is my acceleration. 2 seconds is the time elapsed, right? I should get a final velocity of approximately -11.25 meters per second. I think you can, oh, I guess I'm out of room there on the screen. So meters per second, that's the one that's supposed to be. If we are doing the other one and we figure we're going to 6 seconds, since our acceleration is constant, there's no reason we can't start over from 0 and do this equation again, but using 6 for the time instead of 2. And if we do that, we get negative, okay, what the heck, man? This is getting annoying. Okay, I'm going to write it in blue so it's a little easier to see. But if I redo that calculation at 6 seconds, same setup, but I put in 6 for the number, I should get -3.75 meters per second for my velocity for that one. Okay, let's hope and pray that I think we kept on going on the next slide. Yep, there we go. Wait, calculate the object's displacement from 2 to 6 seconds. Apparently, I didn't. I have no room. Luckily, you've got this one here for you. Calculate the object's displacement from 2 to 6 seconds. Okay, this is where your calculations are really kind of important. And I don't know if this is going to be fine enough for you to see. We're going to do our best. Okay, so we'll stay in blue. And let's consider that from here to here, and then we need from here to here. We need to know the velocities at these different places. So this one is the -3.75 meters per second. Down here, where I have the second blue line is the negative 11.25 meters per second. That becomes important because we need to be able to do this piece for the rectangle, and then we need to be able to do this piece for the triangle as well. So when I do the math for that and I figure out how far the object has traveled, what is it, displacement from 2 to 6 seconds, I am just going to squeeze this up on the top and hope for the best here. Okay, so we are going to take the area of the rectangle, right, this rectangle here, and we're going to add on the area of the triangle below it. Alrighty, so length times width. That's going to actually be my width. I probably should have written that first, all right, but this is occurring over 4 seconds, right? We're going from 2 to 6 seconds, so that's a change of 4 seconds. And then I'm going to do my triangle. My triangle base, now keep in mind, I'm going from here to here. So I'm starting at 3.75 and I'm going to 11.25. That's a change of 7.5. Okay, that's actually negative. Actually, so is this one. That one's negative as well. All right, and again, it's over the 4 seconds. So when I set that up, that's how I'm going to figure out how far I go. And my final answer, when you do that algebra, you should get negative 30 meters. And it should be negative because it's in the 4th quadrant. So don't let that throw you. All right, I'll give you a second there. You should copy that down. And on to the next question, which has nothing to do with that crazy graph. But I need a graph. A car initially at rest accelerates at a constant rate of 4 meters per second squared for 6 seconds. How fast will the car be traveling at that 6 seconds? This is just an application of not just, I'm going to probably need to figure out my delta x here as well, but let's start. Let's start with what I can work with right away. That is the slope of my line. Acceleration is going to be equal to the VF on TF. I took the liberty of canceling out initial velocity and time because they're both 0. So 4 equals VF on 6 seconds, which gives me a final velocity of 24 meters per second here. Oh, that's it. That's all I really wanted to know, right? And oh, I didn't even ask for how far it went. That makes it easy. Yay! But you could find the area under the curve if you had to. Oh, swell. What was I thinking when I did this? I should have squashed this down. Let me see if I can do that. I think I'll pause the recording for a moment and see if I can squash this down for us. So hang on a minute there. All right, we're back. Hopefully that's a little better. There was just no way that was going to work. So figured it was smarter to pause, reposition, and come back. Okay, for each of the position time graphs, draw the corresponding VT-AT motion map. All right, so these dashed lines are representative of when things start to change. Let's consider, all right, position time graph, the slope is velocity. This is a negative velocity because it's a negative slope, but it's a constant slope. So I should have something in the 4th quadrant. That's a nice straight line. And then here I have a velocity of 0 because the slope of my line is 0. So I'm going to go like that for this particular graph. In both cases, I have a constant velocity, which means it's not changing. And here I don't have any velocity at all, so I have absolutely no acceleration. That should be right along the horizontal axis. So it's not going to be perfectly lined up with these little dashed lines, but basically what you should have for the first half of the motion velocity-wise is it should be constant arrows that are all about the same size and then some dots to show that your velocity stops. And we should have just dots for acceleration because we don't have anything for the acceleration. That makes it pretty easy. Okay, let's take a look over. Actually, let's go to the 3rd one. Let's take a look there. All right, so if you consider the difference between the first piece of the graph where you have a curve, the second piece of the graph you have a straight, constantly changing line. So I have a positive velocity because it's a positive slope, but I have a constant positive velocity. Here I have a positive velocity, but I have a changing velocity. It's actually getting more vertical. It's getting steeper, and so therefore I'm getting faster. So what I want to see is that my velocity here should go up because I'm getting faster. It's a positive velocity because it's a positive slope in the position time. I'm getting faster, and then I'm maintaining a constant velocity. Now, the slope of this line, that's the acceleration, and you can see that's a positive slope, so that's a positive acceleration. It is also constant. Here, I have no slope, therefore, I should have no acceleration down there. Okay, if I want to do a motion map for my velocity, what I should see is that I'm going to the right, it's a positive velocity, and I should have tiny arrows. I don't know how well I'll be able to do that here, but I should have tiny arrows getting bigger and bigger. Hopefully you get the drift. For this one, oh, sorry, I forgot. I have a whole second half of motion here. So if I want to keep on going, I need to make the next few about the same size. All right, this is the first half of the motion. There's my second half of the motion. Okay, or actually, I really should put this line not there, now that I've ruined the whole darn thing. Let's see if I can make it close enough. Okay, that's where I should really make it a change, right? Because it's still increasing to this point, and then it's moving with a constant velocity. In terms of acceleration, I should have arrows that are the same size to show a constant acceleration, and then no more acceleration. Oh, for Pete's sake, really? Really? Smartboard stuff is starting to annoy me just a little bit. Okay, I don't know where I had it all. Let's try to line it up right there. Now, stop it. If I yell at it, do you think it'll stop? I don't know. All right, so here's my next one. Here's my last one. I have a positive velocity, but it's becoming flatter. All right, so it's positive, but it is slowing down because I'm going toward a zero slope, you notice. And then here I start with a zero. I don't necessarily have a zero slope, but it's approaching a zero slope. Here I'm starting from a very small slope and I'm getting steeper, and it's negative because my value of the slope is negative. It's going downward, but it's changing and it's becoming more vertical. So this is something that's actually getting faster. All right, this is actually what, like if you toss up the ball in the air, this is what it really looks like as it moves. Okay, we know though that this is where our little bow tie guy comes into play, right? So I'm starting with a positive velocity that's getting slower. I stop, I turn around, and I keep on coming back down again. My acceleration, you'll notice the whole time is negative and it's constant. It's not changing. So we want to keep that in the negative area. Okay, so I'll start with acceleration because that's my easy one. I want them to be about the same size, and I want them to go to the left because I want them to be negative. The velocity one is going to be tricky because this is another one where I have to start like making my arrows tinier and tinier, and then I'm going to turn them around and start making them go bigger and bigger because I'm getting faster and faster for those. All right, we are heading into the home stretch. A little more math. Getting there. We're getting there. Whew. Water skier being pulled by a boat. I'm not going to draw a boat and a water skier. You can do that. You know me, I always draw a darn dot for everything or a box. Okay, but let's say we're getting pulled with a force of 220 newtons. The skier is accelerating at 1.8 meters per second squared. All right, we know we're going to have mg acting on the water skier. You could argue about whether water is a surface. I'm going to say it is. We've got a normal force. She's not certainly sinking or levitating in the water, so we must have balanced forces there. And then we have a drag force, a resistive force. It's actually a type of friction, more or less. And we want to find this one. Okay, it's a pretty standard and straightforward question, but it might take a minute or two to kind of get your bearings as to what you need to do here. Unless you have an acceleration of 0, which you don't, you've got to have unbalanced, you can only have balanced forces if your acceleration is 0. Since that is not the case, we must have a net force, which means that this applies, and it's also equal to the bigger force minus the smaller force. Okay, our smaller force is drag. That's what we want to find. The bigger force has got to be the 220 newtons. Mass times acceleration. Luckily, they gave us the mass in the question. So 80 kilograms. My acceleration that I'm being given is 1.8 meters per second squared. So it's a matter of algebra after that. Okay, so if I do this, I believe I get 144 newtons. Now, full disclosure, at this point in the proceedings at my home, my dog was, I'm not kidding, like trying to stand on my head and get my attention. I was laying on the floor to try to, maybe calm her down, and that didn't work at all. So she kept stepping on things and she kept sitting on my head. So that's amusing, I'm sure, but I don't know if my math is correct. So who knows? We're going to do the best we can. I'm working with the numbers I think I wrote down that were correct. I do believe you should get 76 newtons. You notice what I did there was I simply set up the algebra equation and then I just started moving things around. All right, so first I moved over the drag force, then I moved back over the 144, and that one is set. Okay, this one, we're starting with motion. Notice you're given velocity and time. That to me right away screams VT graph. So 20 meters per second to 5 meters per second. I'm not gonna hit the axis because I'm not coming to rest. But we'll say that's 4 seconds. We want to know not only the average net force, we want to know how far the car traveled when slowing down. So I'm definitely going to have to take the area of those two right there in order to do that. But I need to know the acceleration of the car, which is the slope of the line. If I can find the acceleration of the car, I can find the net force because I know that net force is mass times acceleration. So that part's actually not so bad. All right, so let's begin with the acceleration, which is going to be VF minus VI, TF minus TI. TI is going to drop out. Okay, so final velocity is 5, my initial velocity is 20, time elapsed is 4. This gives me negative 3.75 meters per second squared as my acceleration. So then I'm just going to plug and chug right here. So I've got a 2,000 kilogram car and I've got negative 3.75 meters per second squared for my acceleration. And I'm going to get negative 7,500 newtons for the net force. Okay, when it comes to how far the car travels during this time, again, what I want to do is I want to take the area of this triangle and I want to add it to the area of that rectangle. Okay, so let's start with the rectangle. The rectangle is going to be length times the width. So that's going to be 4 times 5. I'm going from 0 to 5 here. So that's going to give me 20 meters. My area of the rectangle is going to be 1/2 base times height. So 1/2, the base is going to be 4 seconds. The height is going to be 15 meters per second. I want the change from there to there. Okay, so that's going to give me 30 meters. And so my total displacement is going to be 50 meters. There we go. All right, 2 more to go, people. We can do it. We can do it. Next, let's get frisky and put blue on. There we go. All right, rock is dropped from a bridge, 22.5 meters above the water. All right, so actually, never mind. Let's try that again. Just started getting all crazy and stuff. All right, so if here I am at the top of a bridge and I'm going to drop a rock down and it's 22.5 meters tall. Okay, how fast is it going when it hits the water? How long does it take? All right, I guess what I was originally going to work with there was a VT graph, which would make some sense. When you drop something, it starts at 0 for velocity. It goes downward because my acceleration is going to be the gravitational acceleration of negative 9.81. The 22.5 is actually the area under here, and since it's in the 4th quadrant and it's dropping, it's got to be negative. All right, so I don't know TF, and I'm looking for VF as well, which corresponds to, this spot over here on the graph. Alrighty, let's start with area under the curve. It's a triangle, so I've got 1/2 base times height. I'm missing two variables. I'm just going to move the 1/2 out of there, and I'm going to work with the negative 45 equals VF times TF. Then I'm going to work with the slope of the line. And again, whoops, that's a minus. Sorry about that, folks. All right, my TI and my VI are both going to drop out. So I've got negative 9.81 equals VF over TF. If I get TF out of the bottom, which you should, because that will make life a lot easier for you. In the long run, you're going to get that. Now, just in case we have forgotten, we're going to take this value of negative 9.81 TF, we're going to put it right there in our equation. All right, so at this point, what we're working with is negative 45 equals negative 9.81. My TFs are going to multiply together, and I'm going to get TF squared. So I divide by negative 9.81 on this side, and that will give me, all right, I'm just worried about going off the screen here, so I'm going to actually move to the left, which is not ideal. All right, so 45 divided by 9.81 gives me 4.59. I'm going to take the square root of that and get 2.14. Whoops, that's a 1. Sorry, let me rewrite that. 2.14 seconds. All righty. I can take that value for time, and I can quite frankly put it right here and figure out VF. So if I multiply that time by my negative 9.81, I get negative 21.01 meters per second. There we go. One more. We just have one more to go. It's the Skia. Skia going down the hill. Here we are. Okay, free body diagram. MG. Normal. We've got friction, so we must have a coefficient. We've got a coefficient of friction. There's our friction. All right, the incline is 35 degrees. Whew, I'm getting tired after 45 minutes. And mu equals 0.08. All right, so coefficient of friction times normal force gives us friction force every time. That is what we are going to need to know there. We're also going to need to be able to break up our inclined plane. This is our sine piece. This is our cosine piece, our angle of 15 or 35, sorry, I'm thinking of the last question. Our angle of 35 is right there. Okay, so when we first of all, let's do mg. Mg is going to be our mass times 9.81. We're going to get 588.6 newtons for mg. Then we can do mg cosine of 35. So if we multiply that 588 by the cosine of 35, we'll get 482.15 newtons. The cosine piece is also equal to the normal force because we know that that equals that. This skier is not levitating or sinking into the hill itself. Mg sine of theta is going to be 337.6. Again, I'm taking that 588, multiplying it by the sine of 35 degrees. So I get 337.6 newtons for that one. Now, let's consider this is an accelerating body, right? And it is accelerating. I want to do this in a different color because I don't want you thinking I'm putting a force in here. I'm not. All right, it's accelerating down the hill, which tells me that the bigger force is going down the hill. That's going down the hill. This one is the smaller force going up the hill. So mass times acceleration equals the bigger force minus the smaller force. All right, 60 kilogram skier times A equals the bigger force of mg sine theta minus the smaller force of the friction, which I haven't bothered to calculate. Good job, Grady. All right, so 0.08 for coefficient of friction. My normal force is 482.15, which tells me that my friction force is 38.57 newtons. Let's see if I can go around here, 38.57 newtons. So you're going to subtract the right side, you're going to divide it by 60. You should get an acceleration of 4.98 meters per second squared. Final answer. Okay, whoo, that was an exhaustive review for the final. We're going to see quite a bit with graphs. We're going to see quite a bit with motion maps. We're going to see quite a bit with unbalanced forces and balanced forces. So shouldn't be any surprise. We're just going to apply it to a children's story. All right. If you've got questions, come find me, and good luck with studying. All right. Talk to you soon.